The magic of the cyber city. Imagine looking at the top of a cyber city, where every area has a distinct function. From above, you can see the intricate layers connected by a network of ultra-thin copper wires stretching tens of kilometers. This city is unlike any other in the world. It is not built of bricks or concrete, but of sophisticated semiconductor materials. At the deepest part of the city, billions of electronic devices work tirelessly. Digital currents flow through chips, carrying data to perform millions of calculations per second. Among these devices, the most important component is the transistor, a kind of microscopic switch that can turn the current on or off based on the signal received. Today's transistors are extremely small, only about 20 nanometers across, 5,000 times smaller than the thickness of a human hair. On a single chip, we can integrate more than 50 billion transistors. This is truly a technological marvel. Globally, more than 1 trillion chips are produced every year, which means that every second, more than 20 trillion transistors are created. However, this entire incredible manufacturing process takes place in less than 500 manufacturing plants around the world, called fabs. Fabs are complex engineering structures where the most advanced technology is used to manufacture chips. Chip manufacturing, building an entire city at a time. Chip manufacturing is not like mechanical assembly, where each part is painstakingly pieced together step by step. Instead, the world of semiconductor chips relies on a breakthrough technology called photolithography. This is a technique that allows us to create the entire complex structure of a chip, including billions of transistors and microscopic pathways in a single go. Imagine building an entire city of buildings without the need for workers, excavators, or any conventional tools. Everything is done with just light, but not just any light, but light controlled with atomic precision. How photolithography works. Photolithography is the process of using light to etch microscopic designs onto the surface of silicon wafers, the base material for making chips. First, the silicon wafers are coated with a special photosensitive material called photoresist. This is a light-sensitive coating that changes its chemical properties when exposed to specific light rays. The light is then passed through an optical mask, called a mask or reticle, which contains a miniature image of the chip design. This image is shrunk down many times and projected precisely onto the silicon surface using sophisticated lens systems. The light changes the photoresist at the illuminated locations, leaving an imprint of the design. Precision and microscopic scale. The beauty of photolithography lies in its incredible precision. When you hear about the size of a 20 nanometer transistor, you might wonder how humans can create something so small. That's thanks to modern photolithography technology, which can control the wavelength of light to almost the limit of physics. In this process, light is not only used to etch, but also to overcome the natural limits of resolution. This is where technologies like extreme ultraviolet EUV come in. With wavelengths smaller than 13.5 nanometers, EUV light can create microscopic details on silicon surfaces, opening the door to ever more powerful chips. To put that in perspective, think of a modern optical lithography machine as a giant camera, but millions of times more sophisticated. It can miniaturize and project a chip's complex design onto the silicon surface with incredible precision. Chip manufacturing process, from silicon to transistors. Step 1. Preparing the silicon wafer. The chip manufacturing process begins with a basic but crucial ingredient, pure silicon wafers. Silicon is chosen for its ideal semiconductor properties, which allow it to precisely control electrical currents. These wafers are typically cut from pure silicon ingots, huge blocks of single crystal silicon, created in a process called Joukowski crystal drawing. After being cut into wafers just a few hundred micrometers thick, the wafers undergo an extremely thorough cleaning process. First, organic solvents are used to remove any traces of oil, dust, or dirt from the surface. Next, the wafers are soaked in strong acid solutions such as hydrofluoric acid HF or sulfuric acid 2SO4. These solutions not only clean the surface but also remove unwanted natural oxide layers, ensuring that the silicon reaches a completely pure state. After the cleaning process, the silicon wafer is transferred to the furnace. Here, oxygen gas is pumped into an extremely high temperature environment, typically between 800 and 1200. As the silicon reacts with the oxygen, a thin uniform layer of silicon dioxide CO2 forms on the surface. This layer acts like a protective coat, not only protecting the silicon from contamination in the following steps, but also plays an important role in the photolithography process. Step 2. Adding a photoresist. Once the silicon wafer is ready, the next step is to apply a photoresist. This is a special light-sensitive liquid, usually containing polymers and chemical compounds that change properties when exposed to light. The photoresist application process begins by placing a drop of this liquid in the middle of the silicon wafer. The silicon wafer is then placed on a high-speed turntable. The centrifugal force from the turntable spreads the liquid evenly, creating a thin, uniform layer on the silicon surface. The thickness of the photoresist layer can be adjusted by varying the rotation speed or the viscosity of the liquid. After coating, the silicon wafer is baked at a low temperature, usually around 100 C. To harden the photoresist layer, the result is a layer of material that has wax-like properties, but is sensitive to light. This will be the drawing surface. In the next photolithography step, Step 3. Light sculpting. The photolithography step is the heart of the chip manufacturing process, where the intricate patterns of the chip design are drawn onto the photoresist layer using ultraviolet UV light. To do this, the UV light is not shined indiscriminately but must pass through a specialized mask or reticle. The mask is a thin sheet of glass that contains an image of the chip design, with transparent and opaque areas corresponding to areas that need to be etched or retained in the silicon. Ultraviolet light is passed through the mask and complex lenses, then shined onto the silicon surface. These lenses not only ensure that the image on the mask is reduced in size, often dozens of times smaller, but also adjust the sharpness of the patterns. The areas on the photoresist that are exposed to the light undergo a chemical reaction, changing their chemical properties. The silicon is then washed in a special solution. This solution dissolves and removes the photoresist that has been weakened by the light, leaving an exact copy of the mask design on the silicon surface. These patterns are so precise that they can reach sizes of just a few nanometers, smaller than the length of a DNA strand. Step 4. Creating transistors. Once the patterns are etched into the silicon, we move on to the most important step, creating the transistors, the heart of the chip. The process begins by using a reactive gas to etch grooves and windows into the silicon dioxide layer, creating areas that are exposed to the silicon below. Gases such as fluorocarbon CF4 or sulfur hexafluoride SF6 are used in this process, which are capable of precisely etching the silicon dioxide. Next, these areas are colored with chemical ions such as boron B or phosphorus P. This is the ion implantation step, where electrically charged ions are fired into the silicon at extremely high speeds using an ion implanter. These ions change the conductive properties of the silicon, creating two types of semiconductor regions: N-type conducting by electrons and P-type conducting by holes. These semiconductor regions become the basis for transistors, the tiny switches that control the flow of electricity on the chip. A modern chip can contain billions of these transistors, each hundreds of times smaller than a human hair. Craftsmanship at every step. Each step in the chip-making process is a testament to the wonders of science and engineering. From cleaning the silicon, to coating the photoresist, to sculpting with light and creating the transistors, everything is done with incredible precision. Each step has its own unique but indispensable role, like instruments in a perfect symphony. The end result is a tiny but powerful chip that is at the heart of most of the modern devices we use today. Polishing and bonding, preparing for wires. After etching, the surface of the silicon wafer is no longer flat, but rather features like hills and valleys. In order to add the next layer of copper wire, the surface needs to be absolutely flat. This process, called chemical mechanical polishing (CMP), uses tiny ceramic particles and special chemicals to shave the surface flat with atomic precision. This process is repeated hundreds of times, adding layers of transistors, copper wires, and memory storage areas to the wafer. After about 3 months, the wafer is complete, containing hundreds of chips, each a miniature computing city. Fab's environmental challenges. Chip manufacturing not only requires advanced technology, but also a huge amount of resources. A typical fab runs 24/7, consuming millions of kilowatts of electricity every day. The tool chambers must be maintained in a vacuum similar to that of outer space, and the air is constantly filtered to remove dust. Each wafer requires about 5 gallons of ultra-pure water to clean, creating a large amount of liquid waste that needs to be disposed of. Chemicals like PFAS, used in photoresists, are a major challenge. When released into the environment, they can be harmful to human health and the environment. Fabs also emit large amounts of greenhouse gases from the chemical reactions during production. The future of chip manufacturing, combining technology and environmental responsibility. The semiconductor industry is at a critical juncture. As demand for chips skyrockets in the digital age, so does the pressure on manufacturers. Not only do they have to meet high-volume demands, they also face environmental and sustainability challenges. To ensure the industry can grow sustainably in the long term, innovative and comprehensive solutions are indispensable. Environmental challenges of chip manufacturing. Chip manufacturing, especially at fabs, consumes large amounts of energy, clean water, and chemicals. Chemicals such as PFAS, PER, and polyfluoroalkyl substances are widely used in chip manufacturing because of their stability and high heat resistance, but are considered forever chemicals because they do not decompose in the environment. This poses a serious pollution risk if not strictly controlled. In addition, the semiconductor industry is one of the largest consumers of clean water. A large-scale chip factory can use millions of liters of clean water every day to cool and clean the silicon surface. In areas with water scarcity, this becomes an alarming problem. On the other hand, the energy consumption of fabs is also a difficult problem. With the increasing complexity of advanced chips, the amount of electricity required for each manufacturing process increases significantly. Without optimization, the industry will continue to contribute to increasing global carbon emissions.